Hello, everybody, and long time no see. Welcome to a very special episode of, well, it's not even stable diffusion for professional creatives, it's just, I guess, virtual try-ons for professional creatives. Today we'll have an in-depth look for a new virtual try-on that I developed alongside Alex Pugliatti, who will join us in today's video. And it's not really just one singular VTON, but it's a family of models. We will test through HuggingFace space, we will see the technical report on how they were trained and how they work, and then we will have a bit of a nerdy part where we explain how people train virtual try-on models. So first of all, I would like to welcome Alex, who has been working with me for the past year. So hello Alex, welcome, and how are you? And let us know a bit about yourself.
Thank you, Andrea. All good here. About me, I'm Alex. I've worked as a photographer and a designer for the past 10 years for musicians and for many luxury brands, both as a designer and then later on in innovation roles, which is where I started really researching AI and fully transitioning into AI research.
Thank you, Alex. So yeah, we've been working together since a year ago on a number of projects, and then we went on to working together in a startup where we were doing R&D for virtual try-on solutions and other generative AI related stuff. And that's part of the reasons why I couldn't publish any more videos on YouTube, because most of the stuff that we were doing was under NDAs, and so it became increasingly difficult to talk about topics that weren't covered by NDAs or that we weren't working on. But enough of that. These past few months, Alex and I decided to work independently on a virtual try-on solution that started from all that we learned through our endless talks with brands, creative departments, marketing departments, etc. And what they were telling us were their needs in a creative production pipeline. So Alex, can you say a couple of things about where we were starting from, what we were thinking of when we started developing this family of models?
The first thing was always going to be fidelity, because brands have already established production pipelines and they will shoot an image, maybe in real life, and then place the garment onto the person, which makes using tools like GPT-4o or context not suitable for the task, because although it will place a garment that's similar to the original garment on the model, it will also change the entire image. Another obstacle in using the already available VTONs that are out there will be mainly from a dataset point of view, where these VTONs I've been trained on datasets that they only target top, bottom, and full bodies that have never seen accessories and aren't really able to place them on our model.
So yeah, out of all these considerations, what we thought about doing was creating a family of models that could deliver very good results in terms of fidelity while being specialists, each and every one of them, in one product category only. We have a HuggingFace space demo that is available to anyone. I'm starting here with an Alexander McQueen dress on me because I know you're going to try it. But yeah, we have for release these three models: eyewear, footwear, and full body garment. And the way that they work is you just input a base image and a product, and you ask for the correct model. Since they're all specialists, you cannot just mix and match. You need to select the correct model that you want to use, and then you click on generate. And depending on if the model is fully loaded on the backend or not, it's going to take between 20 and 80 seconds. It's all running on Rampart serverless through this Gradio frontend. Of course, it's all based on auto-masking. So in case you upload an image, let's say portrait, and you want to use a footwear model, the workflow is not going to be able to find any segmentation mask for feet, and so it's going to throw an error. And here we have the result. It's same face, same base image, just the eyewear on top. And it doesn't really matter how big or small the image is in the portion that you want to in-paint. For example, with this full body image, we would still get a good result with the eyewear placed exactly where it should be, following the same lighting. And talking about lighting, even in this case where the lighting is very much from the side, we still get a very good and detailed result. Another nice thing about this family of models is that they are really great at keeping details. As you can see here, the details are absolutely perfect, and this is not an easy pattern to reproduce.
And although it's still very experimental, the model seems to be able to also mimic a full look. So you can just take a full body image and try it on. In terms of the other models for top, and bottom. The segmentation models aren't ready yet for release. They will be coming soon after.
And as you can see here, there's a shoe result as well. For shoes, it's usually better to just start with full body images. You cannot just take a shot of your feet and upload it, because otherwise the automasker is not going to be happy with that. These models are currently available through the HuggingFace space and the Gradio APIs, and will very shortly be available as API calls and the SDK through your Mirror.io. Mirror.io is the company that Alex and I are working on in order to bring these models to existing marketplaces, and that's why we have set up API calls and the SDKs so that marketplaces can easily integrate all of this without too much effort. Anyone can sign up to the waitlist and request early access, whether they're brands or not. You can follow the link in the description below to do so.
And of course, before you ask, we're looking at ways to release the model weights for our alpha versions.
So out of all of these considerations, we can see here the final tech report on what we developed and trained. The model family is called sm4ll, and it stands for same methodology for all. And that is actually a very important part of the equation. What we wanted to do is train all different models that were specialists in their own thing while keeping the same methodology. And also it had a nice ring to it. You're gonna find this technical report in the description below. But basically we have these models here and their current status. And as you can see, there's a ton of them, and some of them are more advanced than others, but all of them share the same underlying methodology. And we're gonna see in a bit how you would go training a model like this, starting from an example like CatVTON. We won't bore you with all the technical mambo jumbo. You can read all of that if you want to, but the core methodology is this. We want to have specialized models that have only ever seen the category of products that they're supposed to generate. Then we also want to curate a dataset and prepare it based on how we would handle inference. So the masking process was really, really important in the sense that we couldn't just utilize whatever masking process was best for the dataset itself, but whatever masking process was best for inference. In the wild images, for example, differ greatly from the usual dataset images. So let's say you trained a model on only e-commerce pictures, and then you had users uploading selfies. The same kind of masking that you would do during dataset creation wouldn't be easily reapplicable during inference.
So we employed a training methodology that's inspired by the original extract pics-to-pics paper. And what we were basically doing was showing the model, this is the start and this is the end state. Figure out how to go from step 1 to step 2 based on the instruction given, and focusing only on the region where the painting happens. And then being the comfyui nunchucks that we are, we handled inference through comfyui, using a train like you infer methodology for what concerns masking, which is fundamental in order for the model to understand better the correlation between the product and the person that's the target.
And here we have some results and comparisons between our model family, sm4ll model family, and other competitors like ContextMax, GPT-4o, and CatVTON Flux, and others as well. As you can see here on the left, we have the input images, the product, and the base image, and both Context and GPT-4o slightly changed the images, and that pertains what we were talking about before. In a production pipeline, you cannot go about reapproving images and have slightly different products. Then for other models like CatVTON Flux, for example, you don't get a fair comparison because CatVTON was trained on only top, bottom, and full body images, and it has no idea what eyewear looks like. Our model, instead, a small eye model, is able to faithfully represent these glasses better than any of the other models because it only knows how to do glasses. You can see some more examples here and over here with my face as well. The same goes for tops. Once again, ContextMax and GPT-4o changed the images too much, whereas CatVTON cannot really do a tank top, and Fashion.ai has kind of a bias towards tucking in the top garments and slouching the shoulders a bit. Ours, on the other hand, is pretty faithful to the original. You get some more examples here with the jacket you've seen before, and over here as well with this polo. We got some bottom examples as well, using the bottom model with this short skirt over here as well. And this is, I guess, the funniest since GPT-4o straight up refused to generate the image. We won't annoy you with all the other models. We got dresses as well and shoes. And I think a very interesting part of the research is the qualitative results and creative production pipeline excerpt.
So we actually had some troubles working with Flux context to get some results that were acceptable. Couldn't find a really consistent prompt structure that worked in a lot of cases. Sometimes it was only taking the color of the garment without actually changing the garment. But also Flux context has a ton of compression on the final image, which is then very hard to fix. Instead, when it comes to GPT-4o, which is probably the best in terms of how the actual image looks, although it has this yellow tint that's very recognizable from GPT at this point. It being an autoregressive model, even though it takes the two images as an input and as a reference, it in the end actually changes both of them, creating something that's similar, but it's not the original product and it's not the original image. When it comes to Fashion AI instead, it seemed to be pretty good at actually generating the garment, but suffers from a very big segmentation problem. Then hinders the details of the garments or how it fits. And also Fashion doesn't do accessories, doesn't do glasses or shoes. And then finally, CatVTON Flux, which from our test seemed to be the best in terms of open source VTONs that are out there, performs pretty good in terms of generalization, but as Fashion doesn't work with accessories, doesn't work with glasses, but it's still missing an accuracy on how a garment should fit and details of the garment.
Now, that could be a case for LoRa's, but we have worked a ton with LoRa's. And while they're slightly better in accuracy, the system is not really scalable because you end up having to train a single LoRa for each single product that the brand wants to generate. And that gets very expensive and very time costly very, very fast. The nice thing about basing these models on an instruct pix-to-pix sort of methodology is that they're not really just virtual try-ons. They can also work in other cases, like, for example, face swaps and background generation. Once again, all you need is a training set that tells the model, this is point A, this is point B, figure out a way to get from A to B.
While we haven't yet trained our final version of this model that achieves consistently better scoring than ACE++ or Reactor, it seems to be on its way. In terms of fidelity to the face, it's there. And in terms of FID and clip scores, we're very, very close. It seems to also perform a bit better than ACE++ when it comes to relighting the subject, where ACE++ seems to really mimic the same exact lighting from the input image of the face. That small tends to readapt it based on the context.
And now that the shameless self-promotion is done, well, how do you actually train a VTON model? While you can also take a look at the tech report to understand our methodology, let's take a look at a simpler way to do things. Let's start with CatVTON Flux. Everything you need to know about how to train a Virtual TryOn model is actually laid out in this repo that you can find in the description below. These are the TryOn examples, so the end results. But you can see the methodology here as well, the starting methodology for all VTON trainings. You've got the base image, which is a person wearing the garment, and the garment itself, the still life picture. Now, in the TryOn examples, the result examples, they are inverted. You have the target as the original and the on model as the result. During training, it's the opposite. The result is the base input, and the garment is the base input. Essentially, the model understands how you start from a still life picture and you get to the on model picture. Once it understands the journey to get from point A to point B, it can do so also on starting pictures that do not have the same garment on.
In order to do this, you need a lot of images. We're talking like in the tens of thousands in order for the model to generalize and really understand how to go from image A to image B.
Of course, the results are always going to be as good as the dataset that you get in the training. For example, the VTON HD dataset that was used for CatVTON Flux Alpha had a ton of product images for top garments that were tucked into the bottom garments. So, as a result, the model would have a huge bias towards tucking in top garments.
Yes, exactly. And when it comes to CatVTON Flux beta, it was apparently trained on the dress code dataset, which instead has a huge bias with bags on models, which then end up generating a bag on a lot of generations when the bag shouldn't be there.
And all of this is valid also for poses, for example, or for lighting conditions, all of that. Another thing that you want to be wary of when training a Virtual TryOn model is that if you train on masks that are drawn in a certain way, whether they are automated or not, the model understands the mask rules. And that's another thing that is very hard to predict with CatVTON Flux, for example, because you don't really have access to the correct masks that they end up using. And so when you're drawing masks yourself or using segmentators, for example, Segment Anything 2, YOLO, you name it, you are not guaranteed to get the same results that the model wasn't getting through training, because the masks are not exactly the same. That's why we are putting such an emphasis on getting the masks right during both dataset collection and inference.
So how do you actually construct the dataset? If on one side, you can just reuse VTON HD and dress code, which are not commercially usable. So beware of that. You can go on websites like Kaggle, which host many datasets, and kind of construct your own for what you need, for the task that you need. And of course, even here is the same thing as dress code and VTON HD. You need to be aware of the license and what you can actually do with that dataset.
And once you have the dataset, what you can do, for example, if you want to just take baby steps and do it yourself, you can try training based on the repo for CatVTON Flux using the training script that they provide. You simply git clone the repo and then use the bash command train flux in Paint, of course modifying it to your needs. Now, how to modify that? That's a ton of parameters that can be each interdependent, and that's sort of what's called hyperparameter search. There's a ton of things to be said about that. There's a ton of trial and error, and what we basically did was just spending months trying to find the parameters in our own methodology and get every single thing work nicely together with each other. What I would suggest usually, and the way I work with Alex as well, is just changing one thing at a time and understand what that one thing does.
Yeah, exactly. When it comes to hyperparameter search, is something that most times is more of an art than a science, and it requires a lot of trials. CatVTON Flux, as it is, it's a starting point for you to try things out and test maybe your use cases as well. But it can be something for you to start testing out and see the results that come out of it.
And in terms of hardware, it depends on what you want to train. At what resolution, with which dataset, how many images. It can be as low as one H100 if it's very, very optimized, or it can be as big as 4 H200s tied together with some duct tape and a dream. In case you want to do that, I would suggest using RunPod, since it's not that costly to get access to this kind of hardware. For example, we used a good bunch of H100s, and they're between $2 and $3 an hour, which may seem like a lot when compared to a 4090, but in terms of, for example, AWS prices, it's very, very cheap.
So in order for you to train a VTON-like model, the first thing that you need is a big data set that's made of image pairs, where you have a garment image and a non-model image. Then you bundle all their up, and you need the training script and a GPU for you to actually start the training and start comparing and seeing how much the model is learning, transitioning from the image A to the image B.
And that one is actually the loss. The difference between what you're getting and what you should be getting, the on-model image, is what constitutes the loss of the training process. If you are used to training LoRa's, as I know some of you are, there is a main difference in the process. Whereas with LoRa's, you pair up images to their text files, descriptions, and you feed all of that into a training script. With Virtual TryOn, you want to give the model the same thing, but in two different states. So state 1 is the still life, and state 2 is the same object that is in the still life, but on a person. So yeah, that is mostly all of how you train your VTON and how these models function. You can find these models on HuggingFace Space at the link in the description below. You can find the technical repo in the description below. I want to thank Alex that has been here and has explained some of the behind the scenes stuff that we do day in and day out.
Well, it was a pleasure. Thank you, Andrea. And I hope you guys have fun training your own VTONs or playing with ours.
We hope we didn't scare you away from trying your hands at training your own stuff. Of course, your first results won't be any good, but that's to be expected. There's so many moving parts in training a Virtual TryOn model that makes it much more similar to training and fine-tuning a full model rather than training a simple LoRa. Thank you once again for spending the time watching this video. Sorry for having been away for so long. My name is Andrea Baioni. You can find me on Instagram at Reasonabushi or on the web at andreabaioni.com. And I won't say same as always, see you next week, because we know that's a lie at this point. I guess I will see you when I'll see you. And hopefully that will be soon enough.